Hello, my name is Will Paris, and this is my Physics 2212 Lab for Circuits. This lab was conducted in order to see the behavior of circuits containing different resistors and capacitors with the physical principles of conservation of energy. In order to perform these procedures and calculations, we need a strong grasp of many physics fundamentals, such as conservation of energy, Kirchhoff's circuits laws, steady-state circuits, Ohm's law, resistors and capacitors in parallel and series capacitance, and finally time dependence in resistor-capacitor circuits. In this lab, we are assuming that resistance of wires and ammeter is negligible. So the first part of our experiment has two 1.5 volt batteries, two resistors, 47 and 100 ohms, and two ammeters. And so as we can see, we can use Ohm's law, which is V equals 1 over R. We can find our R, which is the two resistors added together, the resistance R. And then our I, using Ohm's law, we found is delta V over R, and we found that out to be 0.02 amps. And so the data we found after setting up the circuit on the right is that first picture on the left. We found that the ammeter of the first one is 0.0182 amps, and then our current of the second one, I2, is going to be 0.0184 amps. And I'd say that this data was pretty close to the predicted value from math. After replacing the ammeter with a voltmeter, we found the voltage drop to be -3 and the current to be about 20. It was 19.9 in the picture, but about 20, which is 0.02 amps, which is what we found. So for experiment part 2, we test what happens when a battery is connected to a 10 ohm and 20 ohm bulb and capacitor. So when the battery is connected, the light shines, such as in the picture, and then it slowly fades. This is the battery charging. When the battery is disconnected, the light shines again and then goes out more abruptly. This is the battery discharging. We found with the 10 ohm bulb, it took 13 seconds to charge and 13 seconds to discharge, and with the 20 ohm bulb, it took 6.5 seconds to charge and 6.5 seconds to discharge. So for a 9 volt battery and 200 mF capacitor and a 30 ohm light bulb, the experimental RC is 6 seconds. This can be found by graphing ln of delta V versus ln of t, or the linearization of that function over to the right, and then finding the slope. As you can see, it would be RC. The expected RC is found by resistance times capacitance. This is 30 times 0.2, or the 30 ohm light, and the 0.2 capacitor. This is going to be 6 seconds, which is the exact same as our predicted value. Some possible sources of error are most likely human error. So what if you were doing this lab in real life? So actually, we did complete this lab in real life instead of using the software. So we're going to actually flip the question around and ask, what if we did this lab in the software versus real life? So what's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So this can be flipped around, and we could say that in our real life one, the actual current would decrease a little bit. As we could see, ours was about 18 or 0.018 amps. This is due to the resistance of the ammeter. And then if you were doing this lab in real life, how would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So the capacitor would reach full charge immediately in the model, due to there being no resistance if we had no resistor in the circuit. But in real life, this is not the case, because there is some amount of resistance in the wires in the ammeter that we did not account for. So it will most likely take a couple seconds to charge. And that is my lab. Thank you.